So as Kennedy nicely introduced, we're going to be talking about Poisson regression today. So today we're going to finalize our discussion on generalized linear models, and we're going to focus on count data today. And what I want to do today is I want to talk about Poisson, negative binomial, and zero-inflated models. And specifically what I want to do is I want to talk about how we fit and interpret those models in R. I want to talk about visualization of those models. I want to talk about effect sizes and how we might report those type of models. And the running example I'm going to use today is from some work that I did a couple years ago where we looked at stutterers and fixations to faces. So I'm going to talk about some of the eye tracking work that I've done. As always, you can follow along by clicking on this link here, and it'll take you to the Cordo document that you can open up in RStudio. And these are the packages that I'm going to be using for this lecture today. So today's lecture is brought to you by the number 8. So hopefully all of you guys know who this is. This is the Count from Sesame Street. If you don't know, the Count is a very famous character from Sesame Street. I don't even know if Sesame Street is still running today. I know it's probably reruns, but I don't know if there's any new episodes. Anyone, any Sesame Street fans here? Anyone with kids? But his whole shtick is that he teaches children about math and he counts a lot. So I felt like he was a fitting mascot for today's lecture. And a lot of us in here are using count data in our work. So I use count data a lot in the eye tracking work that I do. So I use number of fixations, so how often someone looks at particular images or pictures or words, right? That's count data. And several of you in here are using count data. So Ham, a couple weeks ago, gave an excellent presentation and seminar where he had individuals make bracelets. And I believe they counted the number of motifs that were in the actual bracelets themselves, right? So like, I think it was like 0, 1, or 2 motifs. I don't know if there's anything larger than 3.
At 3, so maybe you could also do like Poisson, like treating everything above 3 as.
Yeah, I think an ordinal regression kind of works there though. So, but yeah, so you're using counting the number of motifs, right? Kennedy, you're counting the number, what was it, number of objects. So that's a count variable. So a DT last semester, you had a project where I believe one of your DVs was number of deviant behaviors, or
what number of like political actions that someone engaged
in. Okay, so number of political actions someone engaged in, but also number of deviant behaviors could be, something that someone is interested in, right? And are there any other folks in here using count data in their research?
I think
yeah.
Confused as to like the difference between count data and just like a continuous integer. Like if I'm counting the like degree in a network or like the number of friends, is that a count or is that just like
that'd be a count?
Okay.
Yeah. So I think the critical distinction is integers, right? Where you can't have non-negative integers, right? And it's not technically continuous, right? Because you can't have like a half a count of something. And I think that's the critical distinction.
But it doesn't matter like how many potential counts you could have. Like theoretically, somebody could list like 100 friends.
Yep.
So that's fine.
Yep. Yep, that should be fine. Yep, I would treat that as a count variable. Anyone else in here using count data? Shall we? You do eye tracking work, right? Do you do like fixations or?
Just making sure the participant is fixating.
Yeah, but like you don't use that as a dependent variable, right? No. Okay. So I use it a lot in my work and the eye tracking work that I do. So there's a whole host of examples of count data in psychology, and a lot of us are using it. So I felt like it was important that we discuss how to analyze this type of data and interpret it. So if we were to actually visualize count data, the count data would look like this. So based off of Kennedy's presentation, visually looking at this, what are some characteristics of this kind of distribution of counts? Just looking at this visually, what do we notice here? What are the characteristics? What was that? Here, just in terms of just like what the shape looks like. But yeah, so in this particular case, lower counts are more often. In this particular, so they're positively skewed. So that's a common characteristic of count data. Anything else? Yeah, so there's no non-negative integers, right? So we have 0, we have 1, 2, 3, 4, 5, and 6 counts. Anything else? So really those are the main things, right? So non-negative, right? So this particular distribution and count data in general is usually bounded by 0 and can theoretically go into infinity, right? There's positive skew and there's non-negative integers, right? So there is no half counts here, right? So it's a discrete distribution. So as I've kind of emphasized over the last few weeks, we need to find a distribution that works well with this type of data. Right, we need something that adequately reflects the data generating process. So what distribution can we use? A popular one is the Poisson distribution. And the Poisson distribution, what we usually say is that the outcome variable here, y, is a number of events or outcomes or counts. And we say that it's distributed as a Poisson distribution with one parameter. And that parameter is lambda. And lambda seems like a scary Greek symbol, but really what it means in this context is just the mean number of counts or the mean number of events. We could easily replace lambda with mu if we want, and I believe Kennedy did that in her presentation. But usually we describe this as just lambda. There's one parameter here. And within the Poisson distribution, what we can do is we can figure out the probability of a certain number of events or counts. And what we could do is we could use this equation right here, which is pretty simple. And it's basically just the exponent of negative lambda times lambda to the y power, where y is the number of events or outcomes or counts, divided by the permutation of y. And y is from 0 to infinity. And there's important characteristics of the Poisson distribution. One characteristic of this distribution is that the mean and the variance are equal to one another. This is assumed. And when I say mean, I mean lambda. The second characteristic of the Poisson distribution is that if lambda is small, the distribution is more skewed to the right. But if lambda is large, it becomes more symmetric and normal in shape. And I've kind of simulated this here where I've increased lambda systematically. So lambda 1 to 5 to 50. And hopefully what we can observe is that lambda 1, the distribution is pretty right skewed. But as lambda increases, we see that it becomes more symmetric or normal in shape, right? So as lambda increases, it becomes more normal. And I also want to emphasize here that lambda determines the mean and the variance. So if lambda is 1, the mean and variance, if we rounded this, is 1. If lambda is 5, the mean and variance is 5. And if lambda is 50, the mean and variance is 50. So within these models, the mean equals the variance. So what type of questions can the Poisson distribution help us answer? Well, we can answer questions about cumulative probability. So let's say that we have an annual number of earthquakes registering at least 2.5 on the Richter scale and having an epicenter within 40 miles of downtown Memphis with a mean of 6.5. So one question we can answer with the Poisson distribution is what is the probability there will be 3 or fewer such earthquakes next year, right? So we're looking at the probability that y is less than or equal to 3. And because we're looking at the cumulative probability, what we need to do is we need to estimate the probability for each event individually. So we need to figure out the probability of 0 earthquakes, 1 earthquake, 2 earthquakes, and 3 earthquakes. And we need to know 2 pieces of information. We need to know the mean or lambda, in this case is 6.5, and we need to know y, which would be the number of events here, right? So 0, 1, 2, or 3. And because we're looking at the cumulative probability, we just need to add all those together here. And I've highlighted that here. And I've showed that we could just plug in lambda and y into these equations here. So that's what I'm showing here with A, B, C, and D. And what we do is just add these up. And we should get the cumulative probability that there will be 3 or fewer such earthquakes. So we could do this by hand, but R has lots of really great distributional functions. So let's just use R. So R has a function called P plus that gives you the cumulative probability. And all you need to enter here is y and 6.5, which is lambda. So y and lambda, and it will give you the cumulative probability of a particular event. So we can run this code here and we'll see that there's 11% probability that there will be 3 or fewer such earthquakes next year. So this is one instance of using the Poisson distribution to get a cumulative probability. The other thing we can use the Poisson distribution for is to get the probability of exact counts. So I have this example here. On average, you read 10 pages an hour. What's the probability you're going to read 8 pages in an hour? We just have to plug in those numbers to that equation. So we have lambda, which is 10. And then we have y, which is 8. And we just plug those into the equation here. Or we can just use another function in R called the d Poisson function that will give you the probability of exact counts. Here, x, we could just say that it's y, 8, and then lambda is 10. And then we can just run this code here, and we get the same answer, which is 11%. So what's the probability you will read 8 pages in an hour? 11%. So this is how we can use the Poisson distribution to get probabilities of particular events or outcomes or counts. So are there any questions just about the generalities of the Poisson distribution? Basically, it's just plugging in numbers. So now I want to shift focus and I want to talk about Poisson regression. So to highlight Poisson regression, I want to talk about a study that I conducted several years ago that was never published because it's bad, but we're going to use it here. What we did is we used this preferential viewing task where we had individuals view faces on the screen. And what we were interested in is what they were looking at. So how many times they looked at those faces, and those faces depicted various emotions. And we were interested in 2 groups of participants. We were interested in a control group, and we were interested in a group of stutterers. So these are individuals that are diagnosed with stutters. And what's interesting is that individuals diagnosed with stutters usually have social anxiety disorder, and they usually tend to focus on negative emotions. So what we wanted to see here is what they look at on the screen, right? When they're presented with faces with emotions. Do they have hyperfixation on negative emotions compared to neutral or maybe more positive emotions? So that's what we're interested in here. So our DV in this particular study was number of fixations to each face. And then what we were interested in is in 2 predictors. We were interested in emotion. So for this particular case, we're interested in angry versus happy faces. So this was manipulated within subjects. So individuals saw all these emotions or all these faces with emotions on them. And then we had individuals that were in the control group or the stuttering group. And this is between subjects variable. So let's go ahead and read in our data here. So we can just run this little bit of code using WebR. Let's go ahead and run that. So what we'll see is a really big data set with lots of columns here. So for this particular example, we're going to do just some data wrangling. And what we're going to do is we're going to select 4 columns. We're going to select the ID column, number of fixations column, the emotion and group columns. And then we're going to filter all the emotions, and we're only going to look at angry versus happy emotions because these are the ones that showed significant effects. So that's the emotions that we're going to look at. So if we look at the actual data frame itself, we'll see that there's an ID column here, and you'll notice that this is in long format here. So we're going to do some multi-level modeling here. So I'm going to show you how to do that. We have a column called number of fixations. So this is the number of fixations to each face. We have an emotion column, which was manipulated within subjects, right? So individuals saw angry and happy faces. And then we have a group column. So individuals were either in the control group or they were in the stutterer group. So if we actually visualize our count variable here and look at the distribution, we'll see that it's kind of prototypically Poisson in nature. So we see that there is non-negative integers here, right? It's discrete. And we do see a little positive skew here. So the Poisson regression or Poisson distribution assumes that the mean and the variance are equal to one another, that there's equal dispersion. So what I've done here is I have calculated the mean and the variance for our data set, and I've also calculated the ratio, the mean divided by the variance. And in our particular data set, the mean is 3.9 and the variance is 3.1. And the ratio is 1.27. Ideally, what we want is the ratio to be 1 or very close to 1, right? Because that's the assumption of the Poisson distribution, that the mean and the variance are equal to one another. In a little bit, I'll show you how we can test for that. And Kennedy already talked about that. There's an over-dispersion test that we can use to see if our data is over-dispersed or this mean equals variance assumption is violated. So we might be really tempted to take this data and just throw it into an ordinary least squares regression, right? And just model it as a linear function of the predictors. But as Kennedy already talked about, this is a bad idea. And there's a couple of reasons why this is a bad idea. One is that if we throw this into an ordinary least squares regression, remember it's fitting a straight line that goes to positive infinity and negative infinity, right? So the predictions might be unlikely given the count data, right? So we don't want to do that, right? And then the second reason is that the ordinary least squares regression assumes homoscedasticity, right? That the mean and the error are constant. With a Poisson or a count data, that's not the case, right? Because the mean and the variance scale with one another. If the mean is 5, the variance is 5. If the mean is 50, the variance is 50, right? So what that does is it leads to, inaccurate interpretations of the coefficients, right? Because it messes with our standard error and also our p-values here. So we don't want to do that. So what we're going to do instead is we're just going to apply a link function where we're going to take lambda, which are just our mean counts, and just apply a log to that lambda value. And then this will allow us to model it as a function of the linear predictors, right? And in this particular equation, each observation can have a different value of alpha, or excuse me, not alpha, lambda, based on this value of the predictors. And then in this particular model, we're not estimating a variance component, right? Because the mean and the variance are assumed to be equal. So we don't need to estimate that separate error term here. So there are several assumptions to running a Poisson regression that we need to test for. One is that it's a Poisson response, so we're dealing with a count variable. The second is independence, so the observations must be independent of one another. The error terms must be independent from one another. In our particular case, this is violated, and this was also violated in Kennedy's example as well. But all we have to do is just fit a multi-level model, and that will take care of that particular assumption. But if we're just running a regular Poisson regression, right, with between subject variables, then we need to make sure that there's independence. Linearity, like our other models, the log of the lambda needs to be linear related to the predictors. And then another critical assumption of Poisson regression is that the mean and the variance must be equal to one another. So there must be equal dispersion. And that's an important assumption to check, because if this is violated, we need to run a different model. So now let's go ahead and fit our model, and I want to go over how we interpret those coefficients. So for this particular data set, what I'm going to do is I'm going to deviation code our emotion and our group variable. So here what I've done is I have taken anger and assigned that to 0.5, and then happy is negative 0.5. And then for the group variable, if you're in the stutterer group, you're going to get 0.5. And if you are in the control group, you're going to get negative 0.5. So if we're going to be running a regular non-nested or non-clustered data set, what we could do is we could use the GLM function like we've used before to model logistic regression. And all we need to do is just change the family to Poisson, and we're going to use a log link here. If we have nested data or correlated data, we have to use a multi-level function. And we're going to use the glimmer function from LME4. So here in the glimmer function here, all we're doing, and the only thing that differs between these two formulas is that we have a random intercept included here for ID. So this is not a maximal model. So little pop quiz here. What do we need to add here to make this a maximal model? Yeah, random slope for what variable? Yep. So if we add a random slope for emotion here, then that would make this a maximal model. But we're not running a maximal model here. We're just going to put in a random intercept model to account for those correlated observations. So if we run this model and like just run the GLM model, the glimmer model, and then do summary output, what we'll have are coefficients that represent the log lambda or the log mean counts. So this is just using model parameters to tidy things up a little bit, but when you run the actual model itself, again, you'll have coefficients like this, and these are going to represent the log lambda or the log mean counts. Log lambda values are not really that interpretable or intuitive, right? So what we could do is we could take those log lambda values and we could just exponentiate them. And what's cool about this is that this gives us mean counts, right? This is something that's more intuitive, that is a little bit more interpretable, right? So last semester I talked about transformations, and I talked about log transformations to reaction times, right? So it's quite common to take a reaction time and log it to make it more normal. But if we exponentiate that log reaction time, we get the reaction time back again, right? So that's essentially what we're doing here. We're taking a log lambda value and we're basically exponentiating it to get that mean count back, to make things a little bit more intuitive or more interpretable. When we exponentiate our log lambda values for our coefficients or our slope coefficients, we get something called the incident rate ratio, or the IRR. And conceptually, this is very similar to an odds ratio, right? So what the IRR tells us is that changes in X affect the rate at which Y occurs, right? So for a 1 unit increase in X, the rate at which Y occurs changes, increases or decreases. So it's the multiplicative effect. So it's basically just an odds ratio, right? And so it's important to note here that when we subtract log values from one another, we're essentially getting the ratio between those two things, right? So that's why this is not a mean count, right? So I just said that if you exponentiate a particular log lambda value, you get the mean counts. Why we're getting this ratio here is because we're basically subtracting log lambda values. And if you subtract log lambda values, we're basically just taking the ratio between those two. But we can get the actual mean counts, and I'll show you how we can do that. But in the coefficients itself, if we exponentiate those coefficients, we usually refer to this as the IRR, the incident rate ratio. It's the multiplicative effect that we have. And if the IRR is greater than 1, then the expected number of events increases for a 1 unit increase. If the IRR is less than 1, then the expected number of events decreases. And if the IRR is 1, there's no difference in the expected number of events for a 1 unit increase. So let's go ahead and interpret our Poisson regression output. So what's really great, so I'm using the model parameters function here, and the model parameters function will actually output like a summary that's really intuitive, because instead of just saying coefficient at the top, it actually lists what it is, which is the log mean. That's a little trick that you can use if just coefficient is not really intuitive to you. But all of these coefficients represent the log mean or the log lambda values here. And if we're going to look at the intercept value here, we get a log mean of 1.35. That's not that intuitive, right? So what we can do is we could just take the exponent of this, and this gives us the mean counts. So in our particular data set, kind of the overall, or at least within the model, the overall mean count is 4. So on average, there's about 4 fixations. That's pretty intuitive. To me at least. So let's go ahead and look at each of our different factors. So let's look at the emotion factor first. So if we look at emotion, we see that the log mean is negative 0.08. So what that means is that angry faces, because we coded them as 0.5, have 0.08 fewer log fixations than happy faces. Or we can exponentiate that value and get the IRR, which is 0.92. So we could say that angry faces have 0.923 times the number of fixations compared to happy faces. And similar to odds ratios, we can just subtract 1 and times it by 100, and we can get the increase or decrease. So we can say that the expected number of fixations is 8% lower for angry faces versus happy faces. Now, it's common to talk about these things in terms of log lambda and the IRR, but what we really want to know is on what's on the original scale, right? We want to know about the mean counts. And what we can do is we can get the mean counts, and we can use M means for this, but what I'm using here is marginal effects. And there's a function called average predictions. And if we put in our variable emotion, what we'll get is the average mean counts for each of our levels. So on average, there's about 3.77 fixations for the angry condition. And then on average, there's about 4.1 fixations for the happy condition, right? This is more intuitive, and I recommend that we talk about these things on the actual response metric, which is mean counts. We can also calculate the marginal effects. So we can get the difference in counts. And we can use the average comparisons function for marginal effects to get the mean difference between those two conditions. And we can look at their significance. So here what we see is that there's a difference of about 0.33. So what this means is that happy faces had 0.33 more fixations than angry faces, or stated differently, angry faces had 0.33 less fixations than happy faces. And this is statistically significant here. Any questions so far on interpretation? So let's look at the group factor. So we see that the log mean is 0.09. So we can interpret this as the stuttering group, because that was coded as 0.5, has 0.09 more fixations than the control group. Or we could just exponentiate that and get the IRR, which is 1.09. So the stuttering group had about 1.09 times the number of fixations, or expected number of fixations, than that of the control group. Or we could say that the expected number of fixations is 9% higher for the controls. And you'll notice that this is not statistically significant, but we're going to interpret it anyways. So we can get the marginal mean counts using the average predictions function. So we see on average there's about 3.75 fixations for the control group, and then on average about 4.1 fixations for the stuttering group. And then we can also get the difference in counts between those two conditions. And the difference is about 0.33, but this is not statistically significant. So how we would interpret this is that the stuttering group had 0.33 more fixations than the control group, but that's not statistically significant. So if we didn't want to use the summary output, we can conduct a likelihood ratio test for our model using the ANOVA function, and we can look at the main effects. So we can just say that the main effect of emotion is significant, but not for group. All right, so any questions so far? Comments, concerns? Now let's get a little bit more complex, and let's add an interaction to our model. So I fit a new model called Model 2 that just includes the interaction between emotion and group, and that's all that's changed from the model syntax. And then this is the output from that model, again, using the model parameters function. So if you just run the summary function in R, it's going to look a little different, but the coefficients to be the same. And if we look at the interaction term, we see that it is statistically significant. So it seems like we have an interaction, but we could do some model comparisons. So we can use the likelihood ratio test to compare a model with just the main effects to a model with an interaction, which we've done before. And if we run the likelihood ratio test, we see that the p-value is statistically significant. So what we can conclude from this is that the interaction is warranted. So we should be including an interaction in our model. So because we have an interaction in our model, we should follow this up with simple effects. So to determine where that interaction is coming from. And we can use the average comparisons function to do this simple effects analysis. So what we're going to do is we're going to look at the difference between the stuttering group and the control group for each emotion. So this is what the by function represents. So we're going to look at the difference between stuttering and control for each emotion. And if we look at the anger emotion, what we see is that there is a statistically significant difference between the stutterers and the controls. And there's about a 0.58 difference. And this is statistically significant. So what we can see is that the stutterers had about 0.58 more fixations than the control group. If we look at the happy emotion, so the difference between the stutterers and the control group, the difference is about 0.03, but that's not statistically significant. So what we can conclude from this is that there's more fixations to the angry faces versus happy faces for the stuttering group. And we can visualize this using GGM means, and you could also use marginal effects. They have a plot comparisons function that you could use, but I like the GGM means function. And what we want to do is we want to plot this data in terms of the mean counts, right? So on the actual response metric. And when we do that, we can nicely see, not really nicely, but we can kind of see, again, this interaction for the angry emotions, right? We see that there's more fixations for the stutterers versus the controls. But we don't see a difference between the controls and the stutterers for the happy faces, right? So this visualizes our interaction, or where that interaction is coming from. So we should check our model assumptions after we've run our model here. And I've output 4 assumption checks for Poisson models. So the first check is called the PP check, which is an unfortunate name, I think, but so it goes. So this basically checks if our model follows a Poisson distribution, as highlighted here. So what we want to see essentially is our observed data, which are these green dots here, contained within the confidence regions of the model predicted data here. And in our particular case, it seems like it's a pretty good fit. All the observed data is within the model predicted data here. So a Poisson model is probably a good choice for our data. We can also check for outliers in our data. We can also check for multicollinearity, but we also need to check for what's called over-dispersion. And Kennedy talked a little bit about this in her presentation, but essentially in a Poisson model, the mean and the variance are assumed to be equal to one another. So if that was the case, what we would expect to find here is that the actual observed data falls right on that blue line here, right? So the predicted mean and the variance would be equal to one another. And in our particular case, it doesn't follow exactly that blue line, but there is kind of like a positive trend, about like a positive slope. So it looks okay, but it's kind of hard to eyeball this type of stuff, right? So there's actually tests that we can conduct and it will tell you if there's over dispersion or not. It's kind of hard to tell from this. So real quick, what is over dispersion? It's when the mean is not equal to the variance. And stated kind of differently, it's when there's more variability in the response than what the model predicts. So I've calculated the mean and variance for the overall model here. And then I've also calculated the conditional effects, so the conditional mean and variance for each of our levels. And as I said before, we want the ratio of the mean and variance to be pretty close to 1, if not 1, because that's what the model assumes. And in our particular case, the ratio, they're fairly close to 1. I don't know if there's any kind of egregious, deviation from 1, but we can test this. There's a function we can use to test this. So easy stats, the performance package has check over dispersion function, and we could just feed our model into that, and it will output a little message that says over dispersion detected or no over dispersion detected. So it's nice, right? But I wanted to go over a little bit kind of what test is being conducted for this dispersion test. But real quick, in our particular model, we see that the p-value is 1, so it's not statistically significant. So it says that no over dispersion is detected. If it was statistically significant, then we would have some indication that there's over dispersion in our model. But the test that's being done basically is it's calculating what's called the Pearson residuals, very similar to the deviance residuals, where we're going to take the observed residuals minus the predicted and divide that by the standard error. And then what we're going to do is we're going to sum all of those up and square them. And we're going to compare this Pearson residual to a chi-square statistic with degrees of freedom equal to n minus p. And essentially what we want are these Pearson residuals and the chi-square statistic to be the exact same. If they're the exact same, then the ratio should be about 1, and that should be indicative of a good model fit. But if there's deviations from that, that suggests that it might not be a good model fit. And that's what this statistic is telling us. So the dispersion ratio should be 1 or close to 1. And the p-value should be non-significant if we have a good model fit. So here we have a pretty good model fit, so there's no over dispersion detected here. But what if we did have over dispersion in our model? What problems can over dispersion cause? So as I said before, the Poisson model assumes that the mean and the variance are equal to one another. So if we have over dispersion in our model, then what's going to happen is that it's going to mess with our standard errors. So it's going to make them smaller, and it's going to make our p-value smaller. So we're going to have increased type 1 error rate. So we're going to say that things are significant when they're not. And I think Kennedy's data nicely showed that, where you don't take account this over dispersion, you have significant effects. And then when you do, those effects go away. So over dispersion matters. And additionally, we're not fitting the correct model. So when the Poisson model assumes that the mean and variance are equal to one another, but if they're not, then we're not fitting the correct model. So we want to fit the correct model. So what do we do about over dispersion in our data? So there's a couple things that we can do to take into account over dispersion. So we can use things like robust standard errors, right? That changes the standard error to account for this inflation. But most popular is using a negative binomial regression model. That's most common. So what I wanted to do is spend some time talking about the negative binomial regression model. And instead of using the Poisson distribution for the negative binomial regression model, we use the negative binomial distribution. And I'm not going to go over the negative binomial distribution. I hate the negative binomial distribution. It's not intuitive to me. But what's important from the negative binomial model are two parameters. So y is distributed as a negative binomial distribution with two parameters, mu, which is basically lambda from our Poisson model, and then it estimates this phi coefficient, which is a dispersion parameter. And what we need to know is that basically it's a Poisson model, but we're estimating this phi parameter. And this phi parameter is important because it is used in the estimation of the variance. So in a Poisson model, we don't estimate the variance. In a negative binomial model, we're estimating the variance. And it's based off of the dispersion parameter that's estimated. And this is the equation for the variance where we take mu, which is the Poisson part, and then we add this quadratic parameterization where we take mu and square it and divide it by the dispersion parameter. So this allows the variance to be greater than the mean. So this is how we're taking into account the over dispersion in our model here. And what's cool about this is that as the dispersion parameter increases, it converges into a Poisson distribution where the mean and the variance are equal to one another. But if we have smaller phi, that means that there's more over dispersion in our model. Again, what I want us to take away from this is that basically it's a Poisson model, but we're estimating a dispersion parameter so we can calculate variance, which the Poisson model does not do. And there's a couple different ways that we can run negative binomial models. So if we have nested or multi-level data like we do in this case, we can use the glimmer.nb function. So this is part of the LME4 package where we usually use to fit multi-level models. And you'll notice here that we're not including an argument for distribution because this model is specific to negative binomial models. So we basically fit a similar model with as we did with Glimmer, but we don't have to add a family to the argument here. And what's cool about these type of models is that we can interpret it the exact same way as we do a Poisson regression. So we run this model, we have a summary output, and we'll get coefficients like this. And these are just the log mean. Same thing with the Poisson model, right? That's what these coefficients represent, the log mean. And we'll see that the actual coefficients are very similar to the Poisson regression. That won't always be the case, but here they're very, very similar. There's not really many differences between this output and the Poisson output. And the p-values and the inferences are the exact same. There's a significant effect for emotion, and there is a significant interaction between emotion and group here. What I don't have included here is when we run this model, there'll be an extra dispersion output. So it estimates the dispersion parameter, which you wouldn't get in Poisson here, but that's not important. The important thing here is that we can interpret the exact same way. And then we can take the exponent of these values and get the IRR, and we can get the mean count, et cetera, et cetera. If we were using a non-nested design, we could use the glm.nb function, which is in the mass package. So this is what you'll be using on Wednesday for the lab. But again, we're just using this glm.nb function to fit the negative binomial model. How do we visualize negative binomial data? Same thing as a Poisson. We show the expected counts. So what I have here is the interaction between anger and happy faces and emotion. And again, we see the interaction here where there's more fixations for the stutterers versus the control for angry faces, but no difference between the two for the happy faces here. So you might be asking, do I run a Poisson model or do I run a negative binomial model? So we can actually do model comparisons because these are nested models, right? So the models are the exact same. The negative binomial model just adds an extra dispersion parameter, right? So these are nested. So we could perform a likelihood ratio test here. And what we see is that the p-value is 9.43. Yeah, so the chi-square test is not statistically significant. So what can we infer from this? What model should we run? Yeah, just the Poisson is fine. And there's some debate, I guess, whether you should just always run negative binomial models. Yeah, so we could run a Poisson model, and I think that would be perfectly justifiable based off of this. But to be safe, we could just also run a negative binomial model. It doesn't hurt. and it accounts for that extra variance. So I don't think there's going to be an instance where like the mean and the variance are perfectly aligned with one another. So the negative binomial model will be able to capture some of that extra variance. So it might be justifiable just to always run a negative binomial model instead of Poisson model. Yeah.
Do we see a case under dispersion? So we see.
Yeah, no, that's a good question. So yeah, so under dispersion does happen, but it's less common than over dispersion. And I actually don't know of any good models that capture the under dispersion very well. I did some research looking at under dispersed models, and I couldn't really find much of anything. In human data and psychology data, over dispersion seems to be more prevalent than under dispersion. Good question. So yeah, so it seems like a Poisson model is okay here. So now I want to talk a little bit about effect sizes in these type of models. So we're fitting a multi-level model here. So we can use the same effect size measures that we use for our linear mixed models we talked about several weeks ago. So we can get our R squared values, so our conditional R squared value, which is the fixed and random effects together, and then also the marginal effects, which is just the fixed effects component. And then we can also compute semi-partial R squared for each of our predictors, which I've done here. So we get the semi-partial R squared for a group and a motion, and then also the interaction piece here. And we can also use the IRR as an effect size measure. That's commonly used in the literature, but we can use all of these things for multi-level models. For simpler models, so if we have non-nested data, we can use the pseudo R squared. So we used McFadden's R squared previously, so we can use that for our models here. We can also use the IRR for individual effects. And I also stumbled upon a package and a Shiny app called RecountD that will calculate Cohen's d for our categorical individual effects. So let's go ahead and click on that Shiny app here. And I think this is pretty easy to use if a reviewer asks for more traditional effect size measures like Cohen's d. What you have to do here is you have to take your summary output, and then you just have to input the intercept coefficient and the standard error of the intercept, and then the regression coefficient for the effect of interest and the standard error for that effect. And then if you're going to do a negative binomial model, just type in the dispersion, and you can calculate the Cohen's d for that particular effect. Again, this might be something that a reviewer requests to make things a little bit more interpretable or more traditional. But I thought that this was a pretty cool package. So you can't really use this for multi-level models, unfortunately. So it's pretty simple models. But if you're running a pretty simple model, then you can calculate Cohen's d for your coefficients. So in terms of writing up your results, what you should be doing is reporting mean counts and marginal effects in text. And then parenthetically talk about log lambda and standard errors, and then your 95% confidence intervals around that, and then p-values, and then the IRR and the effect sizes. And we can use the lovely report function to help us with that write-up. So this is a Poisson model that I fit. And this is the output from the report function here. It gives us all the good bits that we can use for our write-up. All right, so are there any questions about negative binomial models or Poisson models? Do you guys feel comfortable being able to interpret negative binomial and Poisson models? I think it's pretty straightforward. Questions? Kennedy, do you have any questions since you spent a lot of time on Poisson models?
About my data.
All right, so now I want to spend a little bit of time talking about zero-inflated models. So in count data, like in Kennedy's data, there might be an excess of zeros in our model, right? And this can actually be pretty problematic. So excess zeros in our model can cause overdispersion in our data, and excess zeros cannot be solved by using a negative binomial model. And that's because the negative binomial model kind of models all of this as the same process, but it might not be the same process. There might be multiple processes going on in your data, right, that we need to account for. So we need to check for zero inflation. And luckily, Easy Stats is there for us. There's a check zero inflation function that will tell us if our data is zero inflated or not. So in our particular data set, we have observed zeros, so actual zeros, 16 in our data set, and the predicted number of zeros is 23. So it says that the model is overfitting zeros. We have an issue with zero inflation if the observed zeros is less than, or excuse me, if the observed zeros are greater than the predicted number of zeros, then we have zero inflation in our data. And as Kennedy's output showed, it will say you have zero inflation in your data. So if we have zero inflation in our data, we need to account for that somehow. And we account for that by using a zero-inflated model. And the zero-inflated model has two parts. The first part is a count model, and this model is true zeros or sampling zeros. So these are the number of zeros that are expected by chance in your data. And we model this as a Poisson or a negative binomial model. So we just went over how to interpret those things. That's the first part of a zero-inflated model, right? It's just the count part. The second part is a zeros model. And this model is excess zeros or structural zeros. So these are the zeros that are non-random. These are zeros that are a part of your actual data that we might need to account for. And for this part of the model, we use a binomial logistic regression where we model a zeros group. So individuals that are always have a zero versus not zero, right? So we're looking at a zero group versus a not zero group. And we're looking at different predictors that will predict whether you always show zeros or you don't show zeros, right? And I think that there's lots of examples where this type of process is important. So Kennedy talked about some examples from the readings, but I can give another example. So let's say that we're interested in truancy or absenteeism in class, right? There's going to be some folks that never have any absences. They always come to class, right? Do we model that just as a regular binomial or negative binomial? Or do we want to account for that? What predictors influence whether someone comes to class or not, right? I think it's important to figure out that process, right? So there might be things like social economic status that predict whether individuals always come to class or not, right? There might be a whole bunch of factors that influence whether you don't come to class or not. And I think it's important to model that. And zero-inflated models allow us to do that all within the kind of the same mixture model here. Does anyone have any other examples that might work, that might be interesting? So I misrepresented Aditi's work about deviant behaviors, but if she was doing something on a number of deviant behaviors someone engages in, I think it would be important to model this as kind of a zero-inflated model, right? Because it would be important to look at the predictors that influence whether people what are the factors that predict someone who doesn't engage in any deviant behaviors? I think that could be important. This can be important in medical research too. So maybe individuals who just, maybe who don't show any signs of illness or, have not ever had cancer, that would be important to model. And these zero-inflated models can help us do that. So there's two packages that we can use to model this in zero-inflated process. So if we're going to use non-nested data, so between subject variables, we can use the zero-inflated function from the PSCL package. And if we're going to do, if we have nested data or correlated data, we can use the glm.tb package or function, package and function, to model that. And I have two examples highlighted here of how we can fit these type of models. So for the zero-inflated model here, what we're going to do is we're going to model two parts. We're going to model the count part, and we're going to model the zero-inflated part. So here, in the first part here, before the kind of the pipe here, we have the count part, right? So number of fixations, emotion, and group. To the right of the pipe, we have the zero-inflated part. So this is emotion times group. So we're going to look at emotion times group and whether that predicts whether individuals have no zeros versus some zeros. And here we have to specify the distribution we're using. So we're going to use a negative binomial distribution, but we could also use a Poisson if we wanted. And then the link is going to be log. And if you look into the help function for zero inflation, there's a whole bunch of distributions that you can use. So you're not limited to negative binomial or Poisson here. So this is what we would do if we wanted to fit a regular, non-nested model, zero-inflated model. If we want to fit a nested model, we'll use the glm.tmb function. And here there is a formula or an argument called ZI formula, which is zero inflated. And here we can specify the model that we want to fit. And what I've done here is I've just estimated an intercept, but we could add this motion times group variable here too and model that as a function of this zero process. And then the family, there's two types of binomial families here. You could do n binom 2, n binom 1. The n binom 2 function basically models the variance as a quadratic function. So that's what the n binom 2 does. So it just allows us to model this quadratic parameterization. There's also linear parameterization that you could use too, but I usually use just the n binom 2 function. I don't know if there would be differences in the actual results themselves, but. All right, so if we were to run this model and output the results, what we would get is output that has two components. We'll have a count component, and then we'll have a zero inflated component. And the count model or the count component is basically just the binomial or negative binomial or Poisson regression that we just ran, right? The coefficients are the log mean, and then we can exponentiate them and get the IRR, right? So we know how to interpret that. So that should be pretty straightforward. And then the zero inflation component is basically just the logistic regression. So the parameters or the coefficients that are output are the log odds, like with a normal logistic regression. And we can exponentiate those and get odds ratios. So these are things that we already know how to interpret. These are things that we already know how to fit. So now you should be able to run a zero inflated model and be able to interpret the parameters for those models. And then you can use GGM means, or you can use marginal effects to visualize these effects. And in terms of visualization, and I don't have a slide for this, but in terms of visualization, we would want to visualize the count part and then also the logistic part. Again, just combining things that we've already done before, right? So pretty straightforward. So that's all that I have on Poisson, negative binomial, and zero inflated models. If things are a little bit unclear, I highly recommend reading the textbook chapters and the articles. I think that they're really good. Kennedy can attest to that, hopefully. I don't know if you've read the textbook chapters. Oh, okay. But yeah, so I think that those will be helpful for Wednesday's lab. And for Wednesday's lab, what I've done is I've created a pre-registrated document that you're going to read through, and it's up to you to figure out what model to run. So you're going to have to tell me if we need to run a Poisson model or a negative binomial model and provide evidence for that, and then write up the results. So kind of similar to what we've been doing. So are there any questions, comments about count data? Yeah.
So back to the beginning question, I guess the real difference is between whether you use Poisson or ordinal regression is just like, what's the mechanistic model we're seeing?
Yeah.
Okay.
So what you could do is you could fit both. And then you can also look just at the like PP check, or you can look at the distribution to see how well your data fits the model. But I think in your case, an ordinal regression works.
In my case,
So the reason why I think that you wouldn't want to use a Poisson model is because you have bounded data.
yeah.
So it's bounded between 0 and 3. With a Poisson model or negative binomial model, usually it's not bounded in the upper bounds. So it goes into infinity, right? So I think an ordinal regression model would work.
But also ordinal regression does not assume it has to be bound. Right?
Yeah. Mm-hmm.
It makes no such assumption.
Well, I mean, technically it's bounded, right? Because you have 1 and then you have an endpoint, right? So you wouldn't be able to fit an ordinal regression model if you didn't have a bounded endpoint or upper bounds.
I guess the rule of thumb would be that if your data is theoretically bounded, then
Yeah.
ordinal regression otherwise.
So yeah, in a couple of weeks, we're going to talk about, so you're not dealing with like slider scale data, right? Like where individuals have select a point between 0 and 100. But there's a new model that came out probably a couple years ago called the beta ordinal regression, which combines beta regression and ordinal regression. But I don't think that would work in your case because you only have 3 points. But there's a whole bunch of models that you can use in Frankenstein.
It has native value. However, it's kind of discrete categorical.
Like in your case?
No, not in my case. I don't. In my case, you cannot have negative amount.
Yeah.
But just in general, in case of data where you have like integer value that can go to negative.
Then I would probably do like a Poisson or negative binomial type model.
Poisson only applies to positive values.
Yeah. So it goes from 0 to infinity, obviously in the positive direction.
Yeah,
And it wouldn't work if you had negative values.
So what would happen if you have data that you do have negative values?
Then I probably would do like a regular ordinary least squared regression.
Okay.
Yeah.
Even if it's discrete.
Yeah.
Okay.
Or try to do some transformations to it to make it more normal or something. But yeah, in that case, I'd probably do like an ordinary least squares regression model. But some people do take this count data and apply ordinary least squares regression to it. So did anybody read the Poisson fishy paper that I assigned for this week? So it's like Poisson regression, a little fishy, but they do some really cool simulation studies showing that an ordinary least squares regression actually fits the data pretty well in terms of type 1, type 2 error rates, maybe even better than a negative binomial model. So the issue with Poisson is that if you have over dispersion in your model, you have increased type 1 error rate. So what they did is they applied an ordinary least squares regression model and a negative binomial model and compared it. And it seems like ordinary least squares regression works well for count data. So who knows? So if you want to use, ordinary least squares regression on your count data, it's justifiable, I guess. You could just cite this paper and use it. So. Yeah, just everything ordinary least squares regression. But yeah, but we shouldn't do that because we have models that will account for that data. And like cases where we have zero inflation, we have models for that. And we can do some really cool things with that. Whereas with ordinary least squares regression, we can't. We'd have to run multiple models. But good questions. Any other questions, comments, concerns that have come up? So yeah, if you guys don't have any questions, you guys are free to go. And then I'll see you on Wednesday. Oh, and I think Renata and Alex are presenting on Wednesday in seminar, so people should attend.